Imagine a universe where the tiniest moons of our solar system cease to be solitary wanderers and instead merge into a single, colossal dwarf planet. What would such a collision rewrite in the fabric of celestial mechanics? The darkness of space trembles as Deimos and Phobos, the scarred companions of Mars, begin a silent quarrel over their minuscule stature. "I am the smaller," declares Deimos with a dry chuckle. "Yet I orbit farther, so I must be more important." Phobos retorts, "Size matters not when the sun's gravity decides our fate." Their banter, light-hearted as it is, masks a deeper unease that's soon amplified by the distant, patient voice of Ceres. From the asteroid belt, Ceres looms, gravitas-heavy, and poses the central hypothesis. What if every moon in the solar system were to coalesce into a single body? To answer, we must first consider the mass that each satellite contributes. The combined mass of all known moons amounts to a fraction of a percent of Earth's mass. Yet their distribution shapes orbital resonances, tidal forces, and even the stability of planetary rings. If these fragments were to converge, the resulting dwarf planet would possess a radius comparable to that of a small terrestrial world, perhaps approaching the size of Mercury. Its gravitational pull would increase dramatically, altering the tides of the planets it circles. Imagine the oceans of Earth swelling under a new lunar tide, the crust of Mars flexing under a stronger pull, the icy shells of Europa cracking under unfamiliar stress. The immediate consequence would be a cascade of orbital adjustments, as each planet seeks a new equilibrium. But the ramifications extend beyond simple mechanics. A newly formed dwarf planet would retain a mixed composition of ice, rock, and metal, creating a heterogeneous interior. Heat generated by the violent accretion would melt portions of its core, possibly igniting a temporary magnetic field. Such a field could shield nearby planets from solar wind, altering atmospheric loss rates. Over geological epochs, the presence of this massive satellite could stabilize planetary obliquities, reducing extreme climate swings, or conversely, it could destabilize them, leading to prolonged ice ages or runaway greenhouse effects. As the scenario unfolds, the faint voice of Makemake, the distant moon of a dwarf planet beyond Neptune, whispers a warning. The gravitational ballet of the outer solar system is delicately balanced. Introducing a body of this magnitude could eject smaller moons, scatter cometary reservoirs, and even perturb the Kuiper belt, sending icy bodies hurtling inward. The long-term consequence might be an increased bombardment of inner planets, reshaping their surfaces, and perhaps delivering fresh volatiles that could spark new cycles of life. Thus, the merger of the smallest moons into a single dwarf planet is not merely a whimsical thought experiment. It is a cascade of physical, geological, and potentially biological transformations that would reverberate through the entire solar system. As we contemplate this cascade, consider the fragile equilibrium that sustains our world. What do you think about this scenario? Share your thoughts in the comments, but let us turn our gaze to the rocky worlds that cradle life and ask a different question. What if the very dimensions of our home planet were altered beyond recognition? Imagine the Earth reduced to the modest bulk of Mars, its gravity weakened, its atmosphere thinned, its oceans receding to shallow basins. Visualize Mercury, that scorched ember of a world, somehow gaining the mass and temperate envelope of Earth, its surface softened by oceans and a breathable sky. These swaps, though fantastical, illuminate the delicate balance that sustains habitability. If the Earth were to shrink to the size of Mars, its surface gravity would drop to roughly 39% of its current pull. A human stepping onto such a world would feel as if a gentle spring lifted them upward, each stride a light bounce. Yet that very reduction would have profound consequences for the atmosphere. With less gravitational grip, the nitrogen-oxygen mixture that now blankets our world would leak into space at an accelerated rate. Over geological epochs, the protective veil would thin, allowing more solar radiation to scour the surface. The loss of atmospheric pressure would lower the boiling point of water, turning rivers into whispering streams and oceans into scattered lakes. Climate would become volatile, with temperature swings amplified by the diminished heat-retaining capacity of a thinner air column. The magnetic field, generated deep within Earth's molten iron core, would also feel the strain of a smaller planet. A reduced core size would weaken the dynamo, producing a magnetic shield less capable of deflecting charged particles from the sun. The result, a harsher space weather environment, with more frequent auroral displays, but also greater erosion of any remaining atmosphere. Life, as we know it, would be forced to adapt to lower pressure, higher radiation, and a cooler, more erratic climate. Some extremophiles might thrive in subsurface niches, but the complex ecosystems that dominate today would likely collapse. Now reverse the roles. Picture Mercury, that swift, scarred sphere, suddenly endowed with Earth's mass and a generous mantle of water. Its proximity to the sun would still subject it to intense solar flux, but a thicker atmosphere would act as a blanket, distributing heat more evenly across the planet. The day-night temperature contrast, which on present Mercury swings from blistering heat to frigid cold, would be softened, allowing liquid water to persist in stable zones. However, the relentless solar wind, unmitigated by a strong magnetic field, would continually strip away the newly formed atmosphere unless Mercury's core could generate a robust magnetosphere. If it succeeded, a temperate world could emerge, with seas glinting in the perpetual glare of the sun, and perhaps even a nascent biosphere taking root in sheltered valleys. Yet the orbital dynamics would not remain untouched. Mercury's orbital period, already swift, would lengthen slightly under the added mass, altering resonances with neighboring planets. The gravitational tug on Venus and Earth would shift, nudging their own orbits and potentially destabilizing the delicate dance that keeps Earth's climate within a narrow habitable band. A cascade of orbital adjustments could ripple through the inner solar system, reshaping seasons, tidal forces, and even the stability of the asteroid belt that lies between Mars and Jupiter. These thought experiments underscore a central truth. Planetary size, composition, and orbital position are intertwined threads in the tapestry of habitability. A modest change in one parameter can reverberate through climate, magnetic protection, and orbital mechanics, reshaping the very possibility of life. As we contemplate these alternate realities, we are reminded of the fragile equilibrium that permits our blue world to flourish. What do you think would happen if Earth were a dwarf world, or if Mercury became a blue oasis? Would humanity find a way to adapt, or would the very notion of civilization dissolve under new skies? Share your reflections in the comments below, and as we step back from these imagined worlds, consider the broader canvas of our cosmos. Each scenario we explore is a window into the complex physics that governs existence, a reminder that the universe is both resilient and precariously balanced. If these journeys through possibility have sparked your curiosity, stay tuned for the next chapter, where gas giants may ignite their own suns and black holes could devour entire star systems. Subscribe, like, and join the conversation, for together we chart the frontiers of what could be, and perhaps what we must protect.